Event-driven programming is very powerful, but it is greatly enhanced when combined with a concept known as state machines. This combination can tackle almost any problem, yet retain the simplicity and design orientation of event-driven programming. Formerly called finite state machines or finite state automata, these machines are constructs that are used to describe the behavior of a reactive system. Reactive systems, as opposed to transformational systems, are those systems whose inputs are not all available at a single point in time. As events occur, they trigger transitions that alter the state of the machine. State machines are useful when your code must be able to jump to any state at any time and not just execute states in the same sequence repeatedly. They offer more reactive code that can make decisions and remember the past by virtue of their current state. Basically, a finite state machine consists of a set of states and the definition of a set of transitions amongst these states. At any point in time, the state machine can be in only one of the possible states. It moves between the states by transitions in response to events. It may be easiest to understand the concept by examining the graphical depiction known as a finite state diagram or state transition diagram of a simple example. The classic system used to illustrate a state machine is a sequential lock. The correct combination of numbers must be used to open the lock. Here is a state transition diagram for a lock whose combination is 205. Further, there must be a switch that detects whether the door is open or not. In this diagram, the bubbles are states and the arrows are transitions. If we trace the diagram, the system should begin in the locked state, and the input of a 2 on the keypad causes a transition from the locked state to the 1 right state. If 0 is typed next, the transition from 1 right to 2 right occurs. The last step is for the user to enter 5 on the keypad in order to finally arrive at the unlocked state, where in addition to the lights going from red to green, the locking mechanism is deactivated. The act of opening the door would be sensed by a switch that senses the door's position and would transition the system back to the locked state, switching the lights and closing the locking mechanism. There is a problem with this design. Pressing all keys on the number pad repeatedly will eventually open the lock. We need transitions to return to the locked state when a number is pressed out of sequence. The new transitions all have the correct number with a bar above each number. This represents a logical NOT operation and simply means any number other than the correct one triggers the transition back to the locked state. For example, if the user presses 2, then 0, then 8, the machine would transition from the 2 right state to the locked state when the 8 was pressed. While this is much better, notice that the sequence 1205 would open the lock as well. If this is a problem, the transition diagram must be modified further. Events would be used in this case to capture user input. They could be operated by polling the keypad for numeric input or set up as interrupts. Capturing events via interrupts would avoid missed user keystrokes if the state machine portion of the code requires a lot of time to execute. Speaking of interrupts, it might be a good idea to include a timeout feature to the lock. A timer-based interrupt could be added to the code that is triggered a certain amount of time after the machine reaches the 1 right state. If the user does not enter the code in the set time, the interrupt would set a variable indicating the timeout. This timeout transition should be added to the diagram and therefore to the state machine as a condition for transition. This is accomplished by adding OR conditions to the transitions that return the machine to the locked state from the other states along the sequence. At this point, you may wonder about the difference between a state transition diagram and a flowchart. A state machine represents various possible states of a system, whereas a flowchart illustrates paths in program execution flow. A state machine includes the concept of waiting within a state, i.e. waiting for an action or an event to trigger a state transition. Flowcharts do not include waiting as a concept. State machines are useful as modeling diagrams, while a flowchart visualizes branching sequences of a system. One difficulty in creating a programming solution to a problem is the overall structure of the code. The state machine paradigm allows the problem to be broken down into sections or modules driven by the overarching state transition diagram. A program to implement the lock state machine can be written in the Arduino IDE and is posted for reference online. Please be sure to open the program and follow along as it is described. The define statements are directives that tell the compiler to replace the first set of characters with whatever follows. For example, the text locked is replaced with the character A. It is used here to make the code more readable. The names of the states are easiest understood in English, but the state names can only be one character long because the variables used to store the state names are declared as type char, which can only hold one character. So while we may read the state names in the code as locked, one write, etc., the compiler will see them as A, B, and so on. Next, more pound-define statements are used to avoid setting aside memory for output pin numbers, while still referring to the pin numbers with understandable words or names. Two variables are declared and initialized to keep track of the current state the machine is in and to hold the next state determined by the state transition logic. More on that later. The last initialization required sets up a Boolean or on-off variable for each input. The setup function simply sets the pins as outputs or inputs. The first 10 pins, numbered 0 through 9, are connected to a keypad with numbers corresponding to the pin numbers. The 11th pin, pin number 10, has a switch that is opened when the door that the lock is mounted to opens. The next 3 pins are set as outputs for LEDs and the electronic signal that can open the lock. The loop function just repeatedly checks for events, which are button presses in this example. A transition from high to low on an input indicates that a button switch has been pressed, which is an event the code must act upon. Looking at the details of detecting a pressing of the 0 key, the if statement checks to see whether the 0 key is currently pressed by performing a digital read of the pin attached to the 0 key and comparing it to a low signal. If the button is pressed, the comparison will be true, and the program advances to check whether the keypad 0 memory variable is off. If so, that means that the button press has just been detected. The first thing to do is to set keypad 0 memory to 1, or in other words, true. Then it calls the lock state machine function to pass the event that has been detected so that the state machine code can decide what the next state should be based on the event. The lock state machine function will be described later. The code would then continue to check all the other inputs in a similar fashion to detect the event of a switch being pressed. Understand that the code would come back very quickly to checking the 0 key. In fact, it would be so fast the user would still not have released the key and input 0 would still be low. However, this is not a new event because the input did not just transition from high to low. Since the keypad 0 memory variable was set to 1, which indicates that the code has already serviced the event of the 0 key being pressed, the code does not call the lock state machine function again and instead moves to check for events from the rest of the inputs. When the user finally releases the key, the input will become high. At that point, the if condition is not met because the high signal on pin 0 is not equal to low. Thus, the else condition is satisfied and the keypad 0 memory is reset to 0, which allows another key press of the 0 key to be detected as a new event. Basically, the code for each input is set up to detect the transition of the input from high to low, not the level of the input, whether the input is constantly high or constantly low, because it is the transition, not the level, that indicates that a switch has been pressed. Scrolling down locates the lock state machine function, which is where the transitions are computed based on whatever event has been passed to the function in the variable new event. The first statement in the function is a switch statement that selects the case statement that is correct for the current state of the machine. There is no need to compute transitions from a state the machine is not in, only transitions from the current state are required. Assume the machine is in the locked state. The first case is true, so another switch statement evaluates the event that has been passed into the function via the new event variable. If the event was the user pressing the number 2 on the keypad, new event will be the character 2 because that would be the character passed to the lock state machine function when it was called by the code in the loop function that detected the event of the numeric 2 on the keypad being pressed. Since the number 2 is the correct first number of the code for the lock, the next state variable will be set to 1 write indicating that one correct number of the code has been entered. If 2 was not the keypad number pressed, the default case would be true, and the break statement would simply end the switch based on new event. Then the next break statement would end the switch based on current state. After the switch case statements evaluate which should be the next state, the current state variable is set to the next state variable, which was determined by the state machine switch case operations. This, in effect, is what actually changes the state of the machine. Finally, since the outputs are to be driven by the current state, the last section of the lock state machine function sets and clears the appropriate outputs depending on which state is now active. Just remember that the current state of the machine is supposed to drive the outputs. So, for example, the locked state turns the red LED on, the green LED off, and leaves the door locked. An elevator is another potential application for state machines. A simple transition diagram for one includes 4 states: wait, cycle door, moving up, and moving down. Notice that states indicate action. The system begins at the wait state and transitions to any of the other 3 based on whether a request to open the door originates inside the car or any request for service outside the elevator on any floor is received. For the first case, imagine that the open door button is pressed inside the elevator car. The machine transitions to the cycle door state where it presumably opens the door, pauses, then closes the door. For the second case, imagine that a button on the current floor outside the door is pressed. Just as in the first case, the machine transitions to the cycle door state. For the third case, a button outside the elevator, either above or below the current floor, is pressed, requesting service at that floor. The system transitions to either the moving up or the moving down state as required. Note that both of these transitions also require that the elevator was already moving in the requested direction, or, that's a logical or, that there are no other requests. This is for efficient operation and servicing of passengers. Further, notice that these transitions are not simple switch inputs to the system, but require more coding as well as careful thought to decide exactly what they should depend upon. The cycle door state can move to either of the moving up or moving down states, similar to the wait state, and it transitions based on conditions that optimize the operation of the elevator. Finally, the moving states transition back to the cycle door state, since the doors must be opened when a destination floor is reached and the elevator has stopped. Programming the system to recognize when a destination floor is reached is not trivial. So more than just the state machine design is needed to accomplish full operation. The state machine can be expanded to enhance description of the machine's operation. In this design, the acceleration and deceleration phases of motion are assigned their own states for both the upward and downward movements. Note that the transitions are not labeled for clarity of the diagram. However, a bug has been introduced. The transitions from the decel up and decel down states to the wait state are not right. Imagine that the elevator is coming to a stop after arriving at a floor. The doors should cycle open to allow passengers to board or disembark the elevator. Going to the wait state does not cycle the doors. Here, the transitions have been fixed. A very useful feature of state machine design is that debugging can begin before the first line of code has been written. Further expanding the state machine transition diagram allows inclusion of more detail in the door operation. The cycle door state has been replaced by 3 other states: opening door, pausing, and closing door. These states clarify the operation of this section of the machine. But note that adding states to the up and down moving states do not help simplify the transitions that must occur to and from these states.